Hello everyone. Today I, Siddharth Kekre,
I Gargi Bise.
will be presenting our project for CS 5350 Spring 22 on sorting a plentitude of numbers through parallel processing.
In this presentation, we'll be covering the following topics. First, why we need to sort data. Second, introduction to sorting algorithms, namely merge sort and quick sort. Third, performance analysis of sequential and parallel sorting algorithms. Fourth, summary of our experimental findings.
Before getting into sorting of data, the first thing that we need to look at is why do we even need to sort the data? Well, because we have a lot of data. As per Eric Schmidt, the former executive chairman at Google, there were 5 exabytes of information or data created between the dawn of civilization through 2003. But that much information is now created every 2 days. This statement was given by him in 2010, but 12 years later, I guess we have much more data than that. As for the need to sort the data, there are 2 primary reasons for it. The first one is to make sense of all the data we have. As more the data we have, more sorted it is, it's more possible to get information out of it. The second is to perform analysis in an efficient manner. If we have a proper sorted data, we'll have more time and resources to focus on what to do with it rather than just trying to make sense out of it.
There are many sorting algorithms, out of which merge sort and quick sort from divide and conquer family are the most popular and adapted algorithms. Now, let's see what merge sort is. Merge sort is a comparison-based sorting algorithm that employs the divide and conquer strategy. In the divide part, we divide the array into 2 smaller sub-arrays of equal size when the input array is of even size, or the divided part have size difference of 1 when input array is of odd size. Each sub-array is further divided into 2 smaller sub-arrays again and again recursively until we get sub-arrays of size 1. In the conquer part, we then sort the sub-arrays and merge them to produce the sorted array. Through this example, let's understand what merge sort algorithm is. Here, we have an unsorted array of size 7. Implementing the divide part, the input is divided into 2 sub-arrays recursively till we obtain sub-arrays of size 1. Now, let's see how the sub-array are sorted and merged. Here, we are merging 2 arrays that are already sorted by comparing first element of each array, which here is 27 and 3. We will see the smaller element and add it in our array. So we add 3 in the array. The next step would be comparing 27 to 43. So we go ahead and add 27 to our merged array. Then we compare 38 and 43 and add 38 to the array. In the similar fashion, the other sub-arrays are sorted and merged recursively till input data is sorted. To evaluate the performance of an algorithm, we need to calculate time and space complexity. So, time complexity is an approximation of the total number of elementary operations such as arithmetic, Boolean instructions, memory referencing, and many more executed throughout the program. It is assumed that each elementary operation takes a fixed amount of time to perform. Space complexity is the approximate total extra space or memory required by the program to run. Time and space complexities are important because we never want to run a program that exceeds the amount of memory the system has at any given time. It is assumed that each elementary operation takes n units of time to execute. Time complexity of merge sort is order of n log n in all the 3 cases, that is worst, average and best case, as merge sort always divides the array in 2 halves and takes linear time to merge 2 halves. Since the sum of sizes of all sub-arrays is equal to the size of original unsorted array, which is assumed to be n, Hence, the space complexity of merge sort in any case remains the exact same, that is, order of n. Let's see what quicksort is. Quicksort uses a divide and conquer strategy to divide the input array into two sub-arrays. We choose a random element called pivot and we then place it in its correct place and then reorder the array elements by moving all the elements less than pivot to its left and all the elements greater than it to its right. We then recursively sort the sub-arrays of these sub-arrays until the entire array is sorted. Let us understand quicksort through an example. We determine a pivot element in an unsorted array. Then we shift the left pointer to find a value greater than the pivot element. Then we shift right pointer to find a value less than the pivot. Later on, we swap values at the pointers. And we repeat these steps until two pointers both meet or cross. This step is repeated recursively until the entire array is sorted. The time complexity of quicksort algorithm in average as well as best case is order of n log n. In the worst case, time complexity can be order of n square if we select a bad pivot, and it may happen when the array is already sorted in ascending or descending order. Although quicksort doesn't use auxiliary space to store array elements, additional space is required for creating stacked frames in recursive calls. The best and average case space complexity of quicksort is order of log n. This happens when the pivot element's correct position in the partition array is in the middle every time. The size of subarrays will be half the size of the original array. In this case, the recursive tree's size will be order of log n. The worst case space complexity of quicksort is order of n. This happens when the pivot element is the largest or smallest element of the array in every recursive call. The size of the subarray after partitioning will be n-1 and 1. In this case, the size of the recursive tree will be n.
Now, since we know what quicksort and merge sort are, let's implement them through a parallel approach. There are two approaches for parallel sorting. The first one is through multiprocessing and the second one is through multithreading. The multiprocessing approach aims to distribute the task onto all available logical processors such that they all partake in the process through the execution of algorithm. No doubt this would achieve more parallelism and better execution time, but with this approach it is very difficult and time consuming to merge the results from subparts that were distributed among multiple processors, as this approach uses different memory spaces. Whereas for multithreading, it splits the larger tasks into asynchronous subtasks that are executed simultaneously over common memory space that makes the merging of these results from subtasks much faster and efficient. Let's see which packages and frameworks are available for the two most popular programming languages, Java and Python, to implement parallel processing.
Java utilizes the fork join framework in which the fork splits the task into asynchronous subtasks and join is responsible for executing them and merging the results to generate the final result. Unlike thread join method, fork join schedules jobs in much more efficient manner in which the thread may not fall asleep, it will rather switch to another task. This strategy is called work stealing. It allows more efficient use of a limited number of threads. Although fork join is a powerful tool, it should be used cautiously because splitting a small task into smaller subtasks could result in increase in complexity and execution time, unlike what's desired by parallel processing approach.
In Python, the multiprocessor package forks the Python interpreter, and the child process is identical to that of the parent process. For CPU-bound tasks such as sorting, classes within the concurrent features package allow for utilization of both multi-threading and multi-processing approaches. For our project, we have gone for the multi-threading approach because it utilizes common memory space, which is crucial for implementing sorting algorithms over parallel architecture. Since we now know what merge sort and quicksort algorithms are, and also the idea behind multi-threading, let's now understand how to use all those concepts to achieve parallel merge sort and parallel quicksort.
Parallel merge sort is implemented recursively when a root thread divides the elements into two parts and forks two new threads to sort each of them. Then, recursively, each thread divides its element into two parts and forks two new threads to sort them. In parallel quicksort approach, initial list is divided into smaller sublists, which is sent as a task to all available logical processors to sort. Each concurrent subtask finds pivot element and rearranges the list in place.
We have looked into sorting algorithms and implementation approaches. Now, let's see what to expect from these parallel sorting algorithms. As Socrates said, to believe without evidence and demonstration is an act of ignorance and folly, which begs the question, is parallelization actually faster? Because we don't have a proof for it, we only assume that it should be faster. The Amdahl's law provides theoretical speedup in execution of a task at fixed workload for a system whose resources can be improved, based on which Gustafson's law theoretically claims that if a task is run in parallel architecture, then it should execute much faster as compared to being run in a serial architecture system. Theoretical claims aren't going to cut it, so for this project we will look into some experimental findings of our own to analyze whether and which parallel sorting algorithm is worth implementing. Let's look into the performance analysis of sequential and parallel merge sort algorithms in terms of CPU usage, RAM usage, and execution time, where contributing factors such as input data and execution environment are the exact same and there are no running background tasks that would affect our readings. Our code was written in Python 3.6 and was executed on Google Cloud Platform's virtual machine based on Ubuntu OS with 6 virtual core CPU and 120 GB of RAM. Yes, that's a lot of RAM, but we had that allocation as for some scenarios with incorrect coding, we did see up to 80 GB of RAM usage. From the two screenshots shown on screen, the one above depicts system statistics for sequential merge sort and the one below depicts system statistics for parallel merge sort. It can be clearly seen that sequential merge sort utilizes only one virtual CPU, whereas in parallel merge sort, multiple virtual CPUs have been utilized as the bigger task of sorting the entire data has been divided into smaller subtasks and distributed over multiple virtual CPUs. Also, the RAM usage for parallel merge sort is higher than that of sequential merge sort because the program executes multiple sorting tasks in the same memory space. The comparative study was performed by generating 4-byte integers at random and later sorting them. We used 5 sets of data of size 100,000, a million, 10 million, 50 million, and 100 million. The graph presented on screen shows the comparison between execution time in seconds for sequential merge sort and parallel merge sort over the mentioned datasets. It has been observed that parallel merge sort completes the sorting task much faster than sequential merge sort. So it is safe to assume that Gustafson's law states true. Also, note that the execution time down to the last second may vary depending on computation power and latency between CPU and RAM of the execution environment, but the outcome still remains unchanged. Now, we will look into the performance analysis of sequential and parallel quicksort algorithm in terms of CPU usage, RAM usage, and execution time, where the contributing factors such as input data, execution environment are the exact same and there are no running background tasks that could affect the findings. Of the two screenshots presented on screen, the one above depicts the system stats for sequential quicksort and the one below depicts the system stats for parallel quicksort. Just like merge sort, it can be seen that sequential quicksort only utilizes one virtual CPU, whereas for parallel quicksort, multiple virtual CPUs have been utilized as the bigger task of sorting the entire data has been divided into smaller subtasks and are distributed over multiple virtual CPUs. Even the RAM usage aligns with the findings from merge sort, as for the parallel quicksort, it is higher than that of sequential quicksort because the program executes multiple sorting tasks in the same memory space.
The comparative study was performed on the exact same data from merge sort study so that we could later compare performances of these two. The graph presented on screen shows the comparison between execution time of sequential quicksort and parallel quicksort over the mentioned datasets. It has been observed that parallel quicksort and sequential quicksort do not possess distinct difference in execution time. So it is safe to assume that Gustafson's law states false. One prominent reason for the same could be that performance of quicksort algorithm largely depends on the selection of pivot element based on which the input data is divided. Irregular division of data causes irregularity in sorting time. Also, note that execution time down to the last second may vary depending on computation power, latency between CPU and RAM of the execution environment, and selection of pivot elements, but the outcome remains ambiguous.
We will now summarize everything we have seen so far for clear understanding and to obtain presentable results from our comparative study. We performed a comparative study on performances of quicksort and merge sort algorithms in sequential and parallel implementation to know how these perform with respect to each other when presented with similar conditions such as execution environment and input data. The graph presented on screen shows the comparison between execution time in seconds of sequential and parallel quicksort algorithms as dotted lines and sequential and parallel merge sort algorithms as solid lines. Lines represented in blue color represent the sequential implementation, whereas the lines in green color represent the parallel implementation. From what can be observed, for small size of data, that is up to 1 million numbers, the performance differences are not significant. But as the size of data increases, sequential merge sort performs the worst in terms of execution time, whereas parallel merge sort consistently performs the best with increase in input data. As far as quicksort is concerned, the result still stays ambiguous. The graph represented on screen shows the comparison between RAM usage in GB, that is gigabyte, of sequential and parallel quicksort as orange bars and sequential and parallel merge sort as blue bars. Bars on the left represent the sequential implementation and bars on the right represent parallel implementation. From what can be observed, even though merge sort was the fastest, it consumes the maximum memory and is not efficient in terms of memory usage. Whereas the most memory efficient algorithm, that is sequential quicksorts, provides unreliable result in terms of execution time. It's time to conclude everything we have seen so far.
Let's see some key differences between merge sort and quicksort based on their functionality, sorting method, stability, and efficiency. Although both merge sort and quicksort work on the same divide and conquer principle, they handle the partition and sorting very differently. Merge sort performs all the sorting during the process of merging, while quicksort performs most of the sorting in the process of dividing. Merge sort is an external sorting method in which the data that is to be sorted can be stored outside the memory and is loaded in small chunks into the memory for sorting. Quicksort is an internal sorting method where the data that is to be sorted needs to be stored in the main memory throughout the sorting process. Merge sort is a stable sorting algorithm, that is, it maintains the relative order of two equal elements, whereas quicksort is an unstable sorting algorithm, that is, it might change the relative order of two equal elements. The characteristics of the list don't affect the speed of merge sort. If we assume the time cost of comparison and assignment to be constant, merge sort always takes the same time for a particular size of an array. Thus, it is consistent and efficient on any kind of dataset. The efficiency of quicksort largely depends on how we choose the pivot. If the partitions created are very unbalanced, quicksort becomes very slow and inefficient. However, in general, quicksort is very efficient for smaller datasets.
Let's compare the two algorithms, merge sort and quicksort, based on the results that we found from our comparative study. In terms of execution time, parallel merge sort is much faster than parallel quicksort, but the sequential quicksort is much faster than sequential merge sort. As far as RAM usage is concerned, quicksort consumes less memory than merge sort, but with increase in size of dataset, the merge sort's requirement increases much more than what the requirement of quicksort increases. With that, our project presentation has come to an end. The source code and presentation for the comparative study can be found in the description below. Thank you.